Hi everybody, welcome to section 2.3 in Calculus 1. In this section, we'll calculate limits algebraically. So here were some properties of limits or theorems. So the limits of linear function. So pretty much what we see here is the limit of the function, that is the linear function, when x approaching to a, pretty much that is equal to the values of the function. What we learned in the second section is that the limit and the values of the function may not always be the same. But for some certain function, the limit is the same as the values of the function, and like I said, any continuous function will have that properties. Of course, we'll define a continuous function in terms of the limit. That is in section 2.6. We'll get back to that. Before we go there, these are some basic properties of limit. Limit of a sum is the sum of the limits. Limit of a constant multiple is just take that constant outside of the limit. Limit of a product is the product of the limits. Quotient of the limits is the limit of a quotient is the quotient of limits. Of course, when we divide, we cannot divide by something is not equal to 0. And of course, the power. And all of these properties, all of these laws apply to one-sided limit as well. So, to make things simple, of course, when we write like this, each one of them have to be defined. Now, to make things simple, when we look at this second example, you get the idea of what this theorem is really about. So, when we have the limit of, we have the quotient of the difference, so we don't need to go back and look at what rule that we use. The basic about the limit is that when we have the combination of function, all we do is we want to put the limit on each one of them. So first, let me write out the problem. We have f of x, right, minus g of x over h of x. So I'm going to put the limit in front of all of them. Essentially, that's what those rules are about. So just put the limit in front of every single function. Right? And then the question gives us limit of f of x when x go to 2 is equal to 4. Limit of g of x when x go to 2 is equal to 5. And limit of h of x when x go to 2 is equal to 8. So we have negative 1 over 8. Simple enough, right? Once again, in front of every function, we just put the limit in front of it, and doesn't matter how the function are combined. So this one we have 6, and then f of x, I'm going to put the limit when x go to 2. In front of that, each one of them. And then g of x, put the limit in front of that. And then plus h of x, there will be a limit for that as well. And the rest is simple. Put in the numbers. Be 6. Limit of f of x when x equal to 2 is 4. Limit of g of x when x equal to 2 is 5. And then plus h of x when x equal to 2 is 8. So just that, 6 times 4 times 5, 4 times 5, 20, times 6, 120, plus 8, 128. So 6, 5, 4. Yeah. Right. So it doesn't matter how the function are combined. We just want to put the limit in front of every function. And then there's a cube. Yeah. So that's exactly what the rules are about. G of x when x equal to 2 is 5. Cube is 125. Right. So that's simple enough. That's certainly the way to combine limit of the functions. Now, the problem is sometimes we're not given those limits, and that will be a different story. But for now, assume that each individual limits are given, are known, then we'll just combine them. Just like the way the functions are combined. Right, moving on. Now, next, limit of polynomial and rational function. And assume that P and Q are polynomial and A is a constant. So the limit, once again, limit of the function is the values of the function. Like I said, it does not always work. When we're trying to find the limit, not always we put in the numbers, and that is the values of the function. Values of the function has nothing to do with the limit. As we mentioned on the first section, the idea of limit. The idea of limit is when x approaching to something, y approaching to something, and it is approaching, it's not actually getting there. Whether it is happen at the point or not, it doesn't matter. Limit is what the values of the function are approaching to. So it has nothing to do with the values of the function. But for some certain function, the limit is the same as the values of the function. Right. And this rule applies for all continuous functions. So the idea is, for some function, we can just do that. And for most of these examples, except for the piecewise, that's a different story. But for this one, let's put in the numbers and see what happens. If it is a nice number for rational function or polynomial, or pretty much all the function what we know, except for the piecewise function, we cannot do that. But if we just have one function, just put in the numbers. If it is defined, then likely that is the values of the limit as well. So what I do is put in the numbers and see what happens. I'm going to put 2 in. Right. Notice I put in 2. I don't write the equal sign here because I don't know if they are equal or not. Let's see what this equal first. 2 squares 4 times 12, so we have 12 minus 8. And that 2 cubed is 8 times 5, 40 minus 36. So we have 4 over 4 equal to 1. Now, if we have a rational function or polynomial, some even trigonometry, some trigonometric function too. If when we put in the numbers and that turn out to be any number that is defined, like this is defined number, then we will make the limit equal to it. And that's all we do. Once again, put in the numbers and see what happens. If it is the number that is defined, then the limit equal to that. We can do that for every function, polynomial, rational function, square root trigonometry function, pretty much a lot of different functions, except for the piecewise function. We cannot do that because piecewise function, there are two pieces, and we can not do that for piecewise function. Right, let's see, second example. Can we still do that? By the way, yeah, actually, let's just do this first. Put -1 in for x. Right. -1 squared is 1, plus 3 is 4, square root of 4 is 2. And the bottom, -3, -2 is -5. So we have 0 over -5. Now, 0, we have nothing. Divide by -5, still nothing. 0 divided by any number is equal to 0, except when 0 divided by 0. But that's a different story. Now, again, 0 is a defined number. So we just make the limit equal to that. Right, for most of the function, we can do that, except for piecewise function, we cannot. Right, let's see what happened. Of course, we can just graph this and see limits. If we want fraction though, alpha y equal to, that gives us fraction. And we have square root of x squared plus 3 minus 2 over 3x minus 2. Right, we see the graph, and when x is -1, look like that's going to be here. Yeah, kind of difficult to see though. Remember, actually, let's say when x equal to 1, x equal to -1, y equal to 0. Yeah, because the function is defined, and these are the kind of function that we can just take the values of function equal to the limit. Let me emphasize this one more time. For most of the function, if the function is defined, that will be equal to the limit. For most of the function that we know, including polynomial, rational function, trigonometry, exponential, logarithm, if it is defined, that will be equal to the limit. For the piecewise function, never do that. Right, let's find the limit of the function when x go to 1. So we have this piecewise function. Right, by the way, can we graph this piecewise function on the calculator? So let's try. So we know is, just enter exactly -2x plus 4, and then square root of x minus 1. Of course, if you enter like this, it's not going to work because we have the condition of x less than or equal to 1 and x greater than 1. So all we do is just make sure that I have the parentheses around the -2x plus 4. So if you want to graph as the piecewise function or the function with certain condition, just simply open parentheses and we say x less than or equal to. So how do we do that? Second math. And there's we have the values. I mean, the relation. Right. And this one, where x greater than 1. And you should see the graph will look exactly like this. Right. So why it works now? The reason it works because we call the logic operation. Right. Let's take a look at this. If I say 5 greater than 2, then what do you see? What do we say about that? 5 is greater than 2, right? So when we say 5 greater than 2, the calculator will give us 1, meaning that it is true. So if it is true, if we return the values is 1. If it is false, for example, it will return the values of 0. So if it is true, the value is 1. If it is false, the value is 0. Right? So when we look at the function, when x less than or equal to 1, if this is true, it will graph this function. If it is false, it will graph the x-axis, everything will be equal to 0. So if you use in the TI calculator that has color in it, it will not work. It will not look as nice as this. But if it is true, then it will graph the function, take some values. And if it is false, the return of values of 0, 0 times anything is equal to 0. By the way, we can also multiply it. If you use in the TI calculator that has color, instead of multiply, we should do divide. Why do we divide? Because if we divide by 0, it is undefined. If it is undefined, it will not graph anything at all. Right? So, like I said, this is not part of calculus, but I just think that it is interesting, and you might need to use that later. Once again, this relation is true. It will return the values of 1. Anything divided by 1 is itself, so it will graph the function. If it is false, it will return the values of 0. Anything divided by 0 is undefined, so it will not graph anything. So sometimes we can divide, we can multiply, but ultimately the graph will be the same. I should say almost the same. The difference is the calculator, they did not recognize the equal sign. So in the graph, if we actually draw by hand, when it has negative 2x plus 4, for this condition, when it's less than 1, we actually have to have a dot there and an empty circle here. So that is the difference between the two. Yeah, calculator cannot graph a point. They cannot draw an empty circle or a solid point. Right. Now, what we're trying to find is the limit of f of x when x goes to 1. So this is what we're trying to find. Based on the graph, on the left side, y values go to that point, and on the right side, y values go to this point. So the left side limit are different than the right side limit. The function, the limit does not exist, because this is limit equal to 1, which is 1, and we have different limit on both sides. Right? How do we do this by hand? Right. So this is limit when x go to 1, right? So we'll consider the one-sided limit. Usually when we have piecewise function, we have to consider the piecewise, consider the one-sided limits when we talk about the limit at the gap, the gap in the condition. Right, so first, limit when x go to 1, this is less than, so it is from the negative sign. I mean superscript is negative. So if we go from this side, it go to 1 from the left, meaning it's going to be less than 1. And when it is less than 1, we're going to use this part of the function. And now this is a linear function. When we just have a function, if we put in the values and that equal to a number that is defined, so that will be the limit. So I'm going to just put 1 in it. I even don't consider the superscript 1, the superscript negative. So that is equal to 2. Now, if this is a well-defined number, I will make the limit equal to that. I said when we put in the numbers, we don't put in the superscript, because doesn't matter what happened at that point, what is it approaching to. But in this case, it doesn't matter, because this is a linear function. Some certain function have that properties, and I list the function one more time. Polynomial, rational function, any square root or radical function, trigonometry, logarithm, exponential, pretty much everything except for the piecewise function. Now, when trying to find the limit when x go to 1 on the right hand side, so when it go from the right hand side, it's going to be greater than 1, and when it's greater than 1, we use this part of the function. And I put in the number. And that equal to 0. So that is defined. So that's good. So limit from the left is equal to 2. Limit from the right is equal to 0. Because they are not the same. So not the same. So limit does not exist. Right, so that's what we have to do for the piecewise function. Right, let's look at another example. So this we have limit when it is less than 3. We use that function. And when it's greater than 3, we use this function. Once again, in this problem, we're trying to find the limit at 3, which is the gap of the piecewise function. So we have to consider one-sided limit. So first, and this is when less than 3, be from this side. Approaching superscript negative, meaning from the left. And when on the left, it is less than that number. And if it's less than that number, we use this function. And just put the numbers in. I should not write the equal sign here, but it's actually equal to number 5, so it's okay to write the equal sign there. So on the left side, it is equal to 5. And then the limit from the right hand side. On the right hand side, superscript plus, it's going to be greater than that number. And when it's greater than, we use this function. And put in a number. It is 5, a number, well-defined number. So the limit on the right-hand side is equal to 5. Now, those two limits are the same. So we say the limit when x go to 3 of the function is 5. Right, so like I said, when we have the piecewise function and we're trying to find the limit at the gap, we have to consider the one-sided limits. Right. One last thing I want to talk about this problem is that we haven't considered the equal sign, right? And we don't need to, because the limit doesn't matter what happened at the point. It is either less than or greater than something approaching from the left or something approaching from the right. Doesn't matter what happened at the point. Right. But in this problem, if the question asks what is the values of, let's say, f of 1, then whenever the solid dot is, wherever the equal sign is, that gives us the values of the function. So we have the values of the function at 1 is equal to 2, because that's where the solid dot is, and that's where the equal sign is. This is equal to, this has the equal sign, so f of 3 is where the equal sign at. So we just put 3 squared minus 4 is equal to 5. So this case is happened, the limit and the values of the function are the same, whereas here we have the values of the function and the limit does not exist. Right. So bottom line is, for most of the function that I list before, we can just find the values of the function, and that will be the limit. For the piecewise function at the gap, we have to consider one-sided limits. Right. Now let's switch gear to more sample, something else. Right. All the techniques of finding limits. Now let's find the limits of this function. So, of course, first thing, let's put the numbers in and see what happened. So, right, put 2 in for x. Don't write the equal sign yet. Just put in a number. A 2 squared is 4, plus 8 is 12, minus 12, so I have 0 over 0. Then my question is, what is 0 over 0? Remember, I did say 0 divided by anything is 0. Something else divided by 0 is undefined. But what is 0 over 0? So let's write that under the note, what we have. 0 divided by something other than 0 is 0, right? So that's the first one. Next, if we flip them, something other than 0 divided by 0 is undefined. By the way, if you're watching the videos and you did not bring out the note, that's perfectly fine. But what you want to write, might want to write down are the notes, because that's important. The theorem and the definition are nice, but the note is actually the toolbox that we can use. Alright, 0 divided by anything else, 0. Something different than 0 divided by 0 is undefined. And when we have 0 over 0, it could go either way. And we define it to be indeterminate. Which means it can be anything. So when we have 0 over 0, that is indeterminate. So meaning that we don't write the equal sign here, because we don't know if that is actually the case. Don't write the equal sign here. Have to try something else. Right. What's something else we can try? Right. Perhaps you see that both of them can be factored, right? And it is. But how do we factor? That's not that difficult. But this is the nice thing that we can take advantage of. So this theorem is way back in Gauss algebra. It's called the zero factor theorem, meaning that if the polynomial or even the function, if the function when you evaluate at some number equal to 0, then x minus that number is a factor. So I write like this: if the values of the function equal to 0, then x minus that number is a factor. Simple enough, right? And in this case, it's extremely helpful. Alright. So, since when we put when we put 2 on the top is equal to 0, what does that mean? Well, because it's equal to 0, that means x minus that number, minus this number, has to be a factor. So we have 2 and it's equal to 0, meaning that x minus 2 must be a factor on both of them, because both of them equal to 0. That's easy enough, right? Now it is easy to factor if we have one factor. Just need to determine in order to get x squared, so we need an x here. When you multiply now, that gives us x squared. In order to get 8, when we multiply those numbers, the constant out, this has to be minus 4, right? Minus 2 times minus 4 give us 8, right? So it is easier if we know one of the factor, right? X squared minus 4. X squared minus 4, we need x multiply now to get x squared, and we have minus 4, so we need a plus 2, because negative 2 times 2 is negative 4, right? And also it will come in handy later on, difference of 2 square. So in this case we have x squared minus 4, which is x squared minus 2 squared, is equal to x minus 2, x plus 2. Right. Now, but in this case, obviously they have the same factor here, so we can simplify. And then we put 2 in for x, see what happened. So that is negative 2 over 4, so negative 1/2. Sorry, I have a phone call at the middle of the recording section. So I have to answer the phone and have paused the video, and now we continue. So what we are doing is, when we have reduced into this, put in the numbers, and that equal to negative 1/2, which is nice number. By nice I mean it is defined. So we make the limit equal to it. So that's how we find the limit for that problem. By the way, it's always nice to check to see if it actually works. We have x squared, x squared minus 6x plus 8 divided by x squared minus 4. Now when x equal to 2, we cannot do this. We cannot hit trace and we put the values of x. If you put 2 in, there's no value for y. It is undefined at 2. How about 1.99? Yes, close to negative 1/2, which is good. I said we can put a very close number, but we cannot put 2. So numerically we can verify by that. Alright, so that's good. Let's go to the next example. What happens when we have the square root like this? Doesn't matter, right? Put it in numbers. That's the first thing we do. Put it in numbers. If the rational function turn out to be something defined, then that will be the values. That will be the limits. Alright, put 1 in. I just put parentheses when there's access. So 1 minus 1, 0 over 0. So once again, we have indeterminate. And also we say, if both of them equal to 0, then we have x minus 1 on the top, x minus 1 at the bottom, for sure, right? The common factor is x minus that number will be on the top and will be at the bottom. And that's true, yes. However, at the bottom we have x minus 1, which is good, but at the top we cannot get to x minus 1. So, when we have a square root and we try to get rid of that, this is in algebra. If we want to get rid of a factor like this, we multiply by the conjugate. So multiply by the conjugate. And the conjugate is 1 minus, one of them is a plus. And actually the conjugate is the same thing. Those are conjugate. Right. So how did that help? Now it helps, but don't multiply the denominator, because since this is equal to 0 at the bottom, it means it has a factor of x minus 1. So we know for sure x minus 1 will be a factor. So we don't want to mess with it, we want to keep it. Just need to multiply the top. Square root of x times square root of x is square root of x squared. Or we can just write it is equal to a squared minus b squared or x minus 1. But just multiply them. Square of x times 1. Square of x times negative 1. 1 times 1, negative 1. Right. The reason we multiply by the conjugate, because in that case the middle term will cancel out. So we have square of x squared, that gives us x minus 1. At the bottom we have x minus 1 and square root of x plus 1. Can cancel those out. And we have 1 on the top, square root of x plus 1 at the bottom. And now let's put the numbers in and see if that is anything defined. And that is equal to 1/2, which is defined. So we'll make the limit equal to it. So that's nice, right? So whenever we have the square root, if we want to get rid of the square root, multiply by the conjugate. Right, so that's one way to do it. Another way to do this, we can just use these properties directly. Now if we want to use these properties different from 2 square, write, instead of x, I can write square root of x square minus 1 square. And then difference of 2 square what's that? Oh, a square minus b square is a minus b, a plus b. So square of x minus 1 square root of x plus 1. And they share the common factor. When we divide them, when we cancel out, we end up with one over square root of x plus 1, which is exactly what we have at this stage, which equal to 1/2. Right, so that's another way to do that. Either using the conjugate or difference of 2 square, which essentially are the same thing. Right. Let's look at this one. So first thing, of course, put in the numbers, see what happened. Well, indeterminate again. Alright, that means we cannot write the equal sign here. What we can do though, both of them equal to 0. This one doesn't have the square root, so don't need the conjugate. Don't use the conjugate for this. Once again, this is equal to 0 when x equal to 1. So we should have x minus 1 as a factor. Top and bottom. Right, so what is the remaining? The bottom one is easier to factor. X squared minus 5x plus 4. To get x squared, we need x. And to get to 4, we need minus 4. Right. Now on the top, what do we need? Well, it's going to be x squared. Of course, we can do the divide. We just take x cubed. What we can do is we can take x cubed minus 1 divide by x minus 1 and shouldn't have that. But this is later on difference of 2 cubed. So I just want to write this down because this will come in handy. So difference of 2 square is that. Now difference of 2 cubed. And if we have the sum of 2 cubed, so those are the sum of difference of 2 cubed. So the way I memorize this is, look at the sign here. The first one will be the same as those. And then we have the opposite. If that's a minus, not a plus. So same, opposite. And the last one is always positive. Always plus. That's confusing, so. Yeah, so the first one are the same. The second one is opposite. The last one is always positive. It's different from 2 cubed. So in this case, x cubed minus 1 or x cubed minus 1 cubed. So x minus 1 and then a square x square minus, plus ab x times 1 and then plus b square 1 square or just 1, and the common factor cancel out. We will have x squared plus x plus 1 over x minus 4. Right, put in numbers, see what happened. 1 square plus 1 plus 1 divided by 1 minus 4. So that is 3 over negative 3. So that is equal to negative 1. This is a number that is defined, so we'll make that equal to. So limit is equal to negative 1. Of course, if we want to check, we can always just type a function divided by x squared minus 5x plus 4, and then this is trace. Want the limit at 1, right? So we don't put 1 in, obviously. That gives us nothing. That is the graph, it is not 1. If we put 0.999, that's close to negative 1. 1.0001, also close to negative 1. So yeah, so that's good. Or we can look at the graph, it goes to negative 1. The y value goes to negative 1. Right? Yeah, or dividing polynomial, it could be a little bit much. So it would be handy if we know the difference or the sum of 2 squares, or the difference or the sum of 2 cubes here. Right, so that was that. Next, the Sweet theorem. Sweet theorem, it's actually very nice and very easy to understand. However, the application sometimes difficult. I'll explain in a minute. Yeah. So Sweet theorem. Assume that the function f, g, and h. So we have 3 functions. F of x less than or equal to g of x less than or equal to h of x. So it's in that order. Now, if for all values of x near a, except possibly at a, if the outside go to the number, go to the same thing, then the middle go to the same thing, right? So think about this. If we have this in order, if this one go to L and this one go to L, it forces the middle go to the same number, right? That makes perfect sense. In French, I think they call this a sandwich theorem, just like 2 pieces of a sandwich and with a ham in the middle, for example. So if both of them go to the same number, the middle has to go to the same number. So that's why I mentioned earlier, it's very easy to understand. However, the application is difficult, because usually we are not given the outside function. We only given the function in the middle. Our task is to find a function on something bigger than it, easy to find. Find something less than it, also easy to find. What difficult is we have to find something bigger than that, something less than that, but both of them go to the same number. That makes this difficult, right? If we have a number like 1, it's easy to choose a number bigger than that and a number smaller than that. It's almost impossible to work with numbers. But in terms of function, we have to choose some function that is greater than or equal to it and something less than or equal to it. But both of them have to have the same limit. And that's why it makes it difficult. Usually when we see this kind of problem, it's extremely elegant. Right, so here are some examples. Here's something that we can use. Between negative pi over 2 to pi over 2, sine x is between positive and negative absolute values. So let's look at the first one. The graph of sine x. is bounded between absolute value of x, which is the one above, and the negative absolute value of x, one at the bottom. And same thing for this. Like I said, kind of limited application, but when it works, it's extremely elegant. Right, so let's see how it works. Evaluate the following limit. Right, so we only know the function in the middle, so the task at hand is how do we choose the function that is on the right and on the left, but both of them have the same common limit. That's why it makes it difficult, right? Now, actually it's not as bad. Now let's consider this, because we see the graph and we see x squared, negative x squared, but you see that. But let's look at this. What we do know is this graph of the sine function. The graph of the sine function is a wave that is between -1 and 1. Right? So that's what we have. Right, that's nice and all. Now we don't need just that we have the x squared, so I will multiply everything by x squared. Multiply everything by x squared. There's one small thing that we have to consider, is that if we multiply by the number into an inequality, if that number is negative, we have to reverse inequality. Good news is x squared is greater than or equal to 0, so we don't reverse inequality. So multiply by negative, we have to reverse inequality. In this case, we don't have to, because x squared is greater than or equal to 0, so it's positive or 0. It doesn't work. I mean, we don't need to. We don't reverse inequality. Right. So that gives us negative x squared less than or equal to x squared sine of 1 over x squared. So that's why the graph of that function is between x squared and negative x squared. So negative x squared at the bottom and x squared on top. Of course, we can graph that too, but it will look like that. Now the rest is easy. Apply the limit to everything. Right. Limit of negative x squared when x equal to 0. Easy, right? Put 0 into it. It is equal to 0. And limit of x squared when x equal to 0. Put 0 in that. It also 0. Now 0 on the left, 0 on the right. The middle has to be equal to 0. So like I said, when it works, the square theorem is very elegant. But sometimes it's difficult to come up with the function on the left and on the right of it. Right. And with that, we finish section 2.3.